All right, so last time we were looking at the performance of a centrifugal pump, and to quickly refresh your memories, these are two views of a volute type pump. So the fluid will enter axially through the eye in a direction perpendicular to the screen. Okay, so it's a three-dimensional flow. Then it will turn, and the axial component will turn into a radial component and tangential component. Okay, so the fluid will go out through the passages between the impeller blades, which are shown in blue over here. And the impeller will be rotating with the angular velocity omega. So if you look at this view, the fluid will enter axially, and as it goes through the impeller, it will turn. So it will acquire a radial component, and eventually the axial component becomes zero. And then from this point towards this point, that is from the inlet R equal to R1 to R equal to R2 of the impeller region, the fluid will go out radially and it will acquire a tangential velocity. Then it will be collected in the volute and sent out to the discharge pipe here. All right, so we were doing our analysis in a frame of reference which is rotating with the angular velocity of the impeller. And as we argued last time, the flow is steady in this frame. So we showed that the torque is the mass flow rate into the difference of r v theta at the outlet of the impeller minus r v theta at the inlet of the impeller region. And the power is T omega, which is of this form. One can write it as mass flow rate into the rotor velocity at the tip of the impeller multiplied by the tangential fluid velocity, absolute fluid velocity at the tip, minus the same quantities at the inlet of the impeller blade. And since the power is rho q gh, you have the energy transfer gh is u2 v22 minus u1 vt1, and the head you get by dividing the right hand side of this equation 43 by g. So last time we have looked at the ideal characteristics. Assuming one-dimensional flow, we showed that at a constant speed, the characteristic which is the pump, and Q I have written over here for brevity, it is actually a Q flow. Okay, it is a linear curve. So if the blades are radial, as shown here at the exit, that is the angle is angle beta 2 between W2 and minus U, then the head doesn't change with flow rate. If it's forward curved, the angle beta 2 is more than 90. That is, if it's rotating counterclockwise and it is curved in the direction of the flow, in the direction of the rotation, then the slope is positive. And if it's backward curved, so the blade is curved in the backward direction relative to the direction of rotation, then beta 2 is less than 90. And you have a drooping characteristic over here. So this assumption that has been implicitly made is that the flow is one-dimensional. That means that is true if the gap between the blades is infinitesimally small. That means you should have an infinite number of blades. So that is the idealization that we have made. Okay. Now in reality, of course, now why the speed will be constant, you may wonder. Well, usually the impeller is driven by an electric motor, which could be a synchronous motor. And the synchronous speed is determined by the frequency of the AC supply current and the number of ports in the motor winding. And this is a relation similar to what you have seen before in the context of generation of electricity. Okay, the same relation holds over here. So in our country, if you say frequency is 50 hertz, then the speed, synchronous speed in RPM will be 6,000 divided by the number of poles, which must be an even number. Okay. So the speed will usually be constant. Now you may want to know what is the pressure rise across the impeller. Well, one way to get it is, we have already found what is the head. So rho g times head is the difference of the pressure, potential energy, and the kinetic energy. H is the sum of pressure, energy, and potential energy in units of length. Okay, and this H is the difference of H between the outlet and inlet. Okay, so from this relation you can estimate the pressure rise by moving the other terms of equation 559 to the other side of the equation. Okay, and instead of H I can put this difference by G. So using the velocity triangles and assuming one-dimensional flow, you can find out Vt2 and Vt1, and then you can try to estimate the pressure change or pressure rise across the impeller through this. Now another way to do it is to use Moulic equation in rotating coordinates. So we have argued that the flow is steady in a frame of reference which is rotating with the angular velocity of the impeller. So as we have derived before, the sum of pressure, gravitational potential energy, and this is what you may call the centrifugal effect, and the relative kinetic energy, and 1 and 2 will be the same. Okay. So I can rearrange equation 62 and write P2 minus P1 on one side, and you will have the centrifugal effect here and the change in the relative kinetic energy and the gravitational potential energy. Now omega times r is the rotor velocity, the velocity at a point on the impeller. So we can recognize that equation 63 may be written as half rho u2 square minus u1 square. This is the rise in pressure due to the centrifugal effect. So this is what you call a force vortex. In a force vortex, you have only one velocity component, v theta, which is r omega. And in that case, it's easy to show that as you move radially outwards, the pressure increases. And if you have 2 points at radii r1 and r2, the difference will be half rho omega square r2 square minus r1 square. Okay. And this term is the rise in the pressure due to the decrease in the relative kinetic energy. So because the sum here is conserved of relative kinetic energy and other quantities, if the relative kinetic energy decreases, then pressure will increase. Okay. Likewise, if the gravitational potential energy decreases, then the pressure will increase. So this equation is the prediction of invasive flow. But usually the last term, the change in the gravitational potential energy is usually negligible. Now, if you wish, you can move this term to the left-hand side of the equation and write it in the form of a change in the piezometric pressure, P star, which is P minus rho g dot r. So as you can see, to the force vortex effect or centrifugal effect and the decrease in the relative kinetic energy. And if you add to the left-hand side the increase in the absolute kinetic energy, you get the head. So the head I can write in this way as the sum of 3 groups of terms. The first one is the contribution to the head by the centrifugal effect. So because the impeller is rotating and churning the fluid, the head will increase. And as the fluid flows through the passage between the impeller, adjacent impeller blades, the relative velocity, absolute relative velocity, the magnitude of that, W, might decrease. That will increase the head. And of course, the absolute kinetic energy might increase. So that will also increase the head. And I leave it as an exercise to show that the expression for H that we got using angular momentum balance is the same as this. That is not difficult to show. You have to just use some trigonometric relations and the velocity triangle. So this gives you a physical interpretation in terms of energy conversion. All right, now we have seen last time the actual head discharge curve. So the actual head is smaller than what we have obtained as by applying the angular momentum balance and assuming that the number of blades is infinite. So the most important reason why the actual head will be different is because the number of blades is not infinite. So the gap between adjacent blades is finite, and this leads to a non-uniform velocity distribution. Another reason is that there will be frictional losses in the passages. And a third important reason is what we are calling shock or improper relative velocity angle at the blade inlet. So this is something we have shown last time. So this top curve is the theoretical curve, and because of the effect of finite number of blades, you have another straight line predicted by Euler's theory, but this is a more complicated theory, or you have to apply some empirical factors to bring down this curve. And then you have, due to fluid friction, further reduction, and due to turbulence or shock, another reduction. Now, as you can see, the shock loss is zero at the design flow rate. So today I'll discuss in some more detail about the design condition. So this I have touched on last time. In an inviscid flow model, there is no swirl in the pipe and no swirl in the impeller until it reaches the start of the region where you have blades. Okay. So the absolute velocity direction will be radial. So I've drawn the velocity triangle at a point where the radial line is vertical. So the velocity is vertical here, absolute velocity. And if it's rotating, if the impeller is rotating in the anti-clockwise direction, the absolute velocity is this way. So here in the design condition, the relative velocity vector will be tangent to the blades. So the fluid will glide smoothly over the blades. Now, the magnitude of V1 is your VR1, which is determined by the flow rate. So for a given flow rate, and the geometry is fixed, so R1 and V1 are fixed. And U magnitude will depend on the angular speed. So if you keep the angular speed the same and either reduce the flow rate or increase the flow rate from the design value, you get a triangle where this vertical line is either longer or shorter. And if it's shorter, then eddies will form on the suction side of the blade. And if it's larger, eddies will form on the pressure side of the blade. So these are turbulent eddies, and there'll be some loss associated with it. So this loss will be proportional to the square of the difference between the flow rate and the design flow rate, because at the design flow rate, these eddies are not there. So to find the design condition, look at this velocity triangle and see that tan of beta is V1 by U1. And V1 is the design flow rate by 2 pi R1 V1, and U1 is omega R1. So I can rearrange this equation and write the design flow rate as a constant which depends on the geometry of the blades and omega. So for each omega, there will be a design flow rate. If you change the speed of the impeller somehow, then the design condition will change. And you can define a non-dimensional factor called the capacity coefficient, which I call C with a subscript Q, C for coefficient. So that is Q by omega d cube, where d is the impeller diameter. So you can see that I can write it as this non-dimensional quantity here, which depends only on the geometry of the machine. This is a prediction of one-dimensional theory. So this is what you may call the design point or the best efficiency point where the efficiency of the machine will be maximum. So the relation between Q design and omega is a linear relation. So Q design will be this constant CQ design times D cubed times omega. So this design condition is also called the no shock condition, and the pump will have its maximum efficiency at this flow rate, which is the design flow rate. So this is also called the shockless entry condition or the best efficiency point. Okay, now net positive suction head I've already discussed before. Anyway, I will briefly mention this again, that the net positive suction head must be greater than some minimum value to avoid cavitation. And when you apply the engineering Bernoulli equation between a point on the surface of the sump or the upstream reservoir and a point close to the inlet of the pump where the pressure is minimum, this pressure will be less than atmospheric pressure. You see that you have something like this. Net positive head is the atmospheric pressure minus the vapor pressure by rho g minus delta z minus the head loss. Now the head loss is always positive, so you're subtracting a negative number, so that will reduce the NPSH. So the longer the suction pipe, the more will be the head loss, and the less will be the NPSH. If it falls below the minimum value, there will be cavitation. But the other important factor is this delta Z, which we are calling the static suction lift. It is the difference between in elevation between point 1 and point 2. So delta Z is Z2 minus Z1. The height of the minimum point or the inlet of the impeller above the surface of the water in the upstream reservoir or sump. Now, I've shown a figure where delta Z is positive. But if the pump is very long, then you may want to make delta Z negative. That is, you want to put the pump, locate the pump below the level of water in the sump. And you have this Thermo cavitation parameter, the NPSH by the head developed by the pump, which must be greater than some critical value to avoid cavitation. So to ensure this condition, sometimes the pump may have to be placed below the reservoir. Now let us look at the dimensionless performance of the pump. The variables that are of interest are the head developed by the pump and the power required to run the pump. And the variables that control these quantities of interest are obviously the discharge or flow rate, Q flow, the shaft speed, and the impeller diameter. There will be other variables also, which I am calling secondary variables for reasons that I will discuss later. It has the fluid properties and the roughness of the impeller surface. So I put the variables which control the head and power into two groups, two categories, which have 3 dimensional variables. So total there are 6 dimensional variables. So the energy transfer I can write as a function I'm calling F subscript H for head, and the functional form of P I'm writing F subscript P. So each of them, these functions have 6 arguments. So there are 7 dimensional variables involved. And using dimensional analysis, you can find the non-dimensional parameters. The important ones I'll just state here. One is called the head coefficient. It is GH by omega squared D squared. See, omega is in radians per second, so units is 1 by second. Omega into the diameter is meter per second. So this has units of denominator here, has units of meter per second whole square. And numerator is meter into meter per second square. So this is non-dimensional. Now GH is the energy transfer per unit mass flow rate, so it is also called sometimes energy coefficient. But this term's head coefficient is more common, So I put the subscript capital H over here. So this C, capital C, denotes coefficient. It's a non-dimensional quantity. Similarly, you have a power coefficient, which is the power by rho omega cubed d phi. Now, I have used omega here. Authors of some textbooks will use the symbol capital N for the speed. But I have used N for the speed in RPM and omega for the speed in radians per second. So to get it in non-dimensional form, we should use omega. So omega is 2 pi n by 60. They are related. Likewise, you have a flow coefficient or a capacity coefficient, which is the volume flow rate by omega d cube. So again, this is 1 by second and this is meter cube. So denominator is meter cube per second. So this is non-dimensional. And if you look at the fluid properties, then you will have a Reynolds number using a velocity which is omega d. And you also have the roughness ratio, that is the average roughness height epsilon by the diameter of the impeller. So in your second year course, you must have studied about Moody's chart, and you know for turbulent flows, the friction factor is affected by epsilon star. So the non-dimensional functional relation for head, so number of dimensional parameters here is 6, and there are 3 dimensions. So the number of non-dimensional parameters here will be 3, controlling the dimensionless power and the dimensionless head. So the 3 relevant ones I can write. So I've written capital F H here because it's a non-dimensional functional form. So CH will depend on CQ as well as RE and epsilon star. Now likewise, you can look at the functional relationship for the power. Then the power coefficient will be another function which I'm calling capital F of P of the same 3 quantities, CQ, RE and epsilon star. Now the efficiency, overall efficiency of the pump is the energy that is imparted to the fluid rho QGH by the power input to the pump. Now I can write Q flow as CQ times omega d cube. GH can be written as CH times omega squared d squared, and P can be written as CP times rho omega cube d phi. So you see that the eta for the pump, the efficiency is CQ multiplied by CH by CP. Now in most cases you'll find the Reynolds number is high, of the order of 10 to the power 7. So the flow is highly turbulent. At such high RE, you find that the variation of CP and CH with the Reynolds number and this roughness ratio is small. So these have some effect, but it's a constant effect. That is, variation in the RE does not affect the flow rate, the CP and CH when the RE is large. When the RE is low, it will have an effect. And when the RE is large, the variation of epsilon by d also does not have any effect. So we can conclude that there's only one non-dimensional parameter which controls non-dimensional head coefficient and the non-dimensional power coefficient. So you can say this, of course, is an approximation for large RE, but this is what we have in practice. And since eta depends on CQ and CH, which depend in term, and CP and CH depend on CQ, you can say that the efficiency also depends on CQ and CQ only. So the good news is that although there are 3 parameters, 3 non-dimensional parameters, which can affect the quantities of interest, only one of them is relevant when the Reynolds number is large. That is what you have in practice. Now this I have left as an optional exercise. You can start with the given functional relationship in dimensional form and determine the equivalent non-dimensional functions using the method of repeating variables, which you have studied in your second year. So I left it as 2 optional exercises, one for the head and one for the power. Now, another important non-dimensional quantity is what is called the specific speed, or some people call it the type number. All right, any queries? Okay. Now, you know that combinations of non-dimensional parameters are also dimensionless. So can we find a combination which is independent of the size, but just depends on the shape? Is directly proportional to omega, because that is a important control variable. So the important parameters are the head coefficient and the capacity coefficient. So consider a combination of this form, this non-dimensional CQ raised to power m, and where m is a constant, and multiplied by the non-dimensional head coefficient raised to the power n, where n is another constant. So I can write it in this form. The power of omega will be minus m plus 2n. The power of Q flow will be m. The power of h will be n. And d will have this power. Now we want to eliminate d from this combination. So we can choose m and n such that the exponent of d, the last term on the right hand side of equation 104, is 0. Then you will have d to the power 0 or 1 in the denominator. And you want this quantity minus of m plus 2n to be equal to 1. So m plus 2n is minus 1. Then this combination will have omega raised to the power 1 times something raised to the power into Q flow raised to some power into GH raised to some other power, and no d in it. Okay. So you can solve these two simultaneous equations. Details are not given in any book. I've given you the details. So what you find is CQ raised to the power half divided by CH raised to the power 3 by 4 will be another non-dimensional parameter where there is no d in it, and the power of omega is 1. Okay, and this is what is called the dimensionless specific speed of the pump. Okay, it is CQ to the power half by CH to the power 3 by 4. So almost all the books that you will come across will just state this. I've given you the derivation. So it is omega into square root of Q by GH raised to the power 3 by 4. Now, the shape of a pump is characterized by the efficiency and by the specific speed for the maximum efficiency conditions. So you want the pump to run in the design condition or the shockless entry condition or the no shock condition where the efficiency is maximum. Some people call it the best efficiency point. So the specific speed will determine at this point, best efficiency point will be determined by the shape, not the size. So you can have self-similar pumps where the impeller are geometrically similar in shape, but the diameter will be different. Okay. So your job as a designer is to find the shape, and today people will use techniques of computational fluid dynamics to do this. And then you may perform experiments using models and dimensional analysis to check out your prediction of the numerical method. Okay. Now, sometimes people define something called a suction specific speed, where instead of h, they put NPSH. And it has been observed that if omega suction falls to about 3, then cavitation starts. So you should ensure that this omega suction for your pump when it's running is greater than 3. Now another point which causes confusion is that people talk about a dimensional specific speed. Since g is a constant, people remove g from the definition. So I've written it here for the sake of completeness. I've called it n tilde s, which is n times square root of q by h to the power 3 by 4. Now obviously the value of this will depend on the system of units that you use. So if you are referring to a handbook or some other reference on paper, you have to see what units the author has used. And typically they'll use N in RPM. So this multiplied by some constant factor will make it non-dimensional. Okay. And the non-dimensional thing, needless to say, is independent of the system of units that you have used. Okay. So if you want to be elegant from a scientific point of view, one should use the dimensionless quantity. Okay. But practicing engineers who refer to handbooks may be doing it in dimensional form, so you should be aware of this. Now, if you have two pumps where the impeller shape is the same, so they belong to the same geometric family, but the sizes might be different, that is, the impeller diameter must be different. If they are operating at homologous points, then you can predict the performance of pump A by looking at the performance of pump B. So homologous point means that if you non-dimensionalize the quantities, then you will be at the same location in a non-dimensional graph. So here the important factor is the CQ. So if CQ for pump B and CQ for pump A are the same, then if the CP for pump A, because when the Reynolds number is large, the effect of Reynolds number and the roughness ratio can be neglected, and you can say that CH depends only on CQ and CP depends only on CQ. So if CQ for the two pumps are the same, then this will also be the same, but of course they also have to be geometrically similar. So these are things that you have studied in your second year. Here is an important application. So if we equate the flow coefficients, you see that the ratio of the flow rates, so here I have not written the Q flow superscript for brevity. It is omega B by omega A ratio into some size parameters coming. So you could have a case where both the pumps have the same speed, so this ratio might be 1. But suppose 1 dB is twice of dA, then the flow rate for the homologous point will be 8 times QA. Okay. And if you look at the head, it will be 4 times. And if you look at the power, it will be 2 to the power 5 or 32 times. Okay. So this similarity rules have been made simple by the fact that in practice the Reynolds number is large. So there is only one parameter which controls dynamic similarity, assuming of course that the two pumps are geometrically similar. So we can use these rules, similarity rules, to estimate what will happen if you change the rotational speed or the size of a pump within a geometrically similar family of pumps. Okay. So I've given a simple exercise which you can go through later on. Now let us talk about what are called affinity laws. So if we have looking at different running conditions for the same pump or an identical pump, then the impeller diameter is fixed. So then the flow rate will, in dimensional form, will be proportional to the angular speed. The head developed by the pump will be proportional to the square of the angular speed, and the power will be proportional to Q when the conditions are dynamically similar. So these are called affinity laws. So for example, if you know the characteristic at one speed, say n equal to n1, suppose I plot H versus Q here. So this Q is the flow rate. Okay. And I want to predict the results at n equal to n2, which is say n1 by 2. Okay. So I have looked at 2 points here, O and O prime, which I am calling homologous points. So if you find the flow coefficient at point O and the flow coefficient at point O prime, they will be the same. Now the diameter is the same. So if you have halved the speed here and kept CH the same, that means Q will also be halved. Okay. So if you know the head here, you can find the head here. This will be then 1/4 of this head. Okay. So likewise, you can take several points on this characteristic at speed n equal to n1, and you can predict the characteristics at another speed. Of course, assuming that the Reynolds number is large. So I've given you another simple exercise which you can look at. Now, let us look at a practical problem. Suppose you are using a centrifugal pump to raise water from a tank at lower level to a tank at a higher level. So I've indicated here a datum and a z coordinate pointing upwards. So g is a gravitational acceleration pointing downwards. So this is a schematic of the pump. This is the suction pump. Okay. And this upstream reservoir is called the sump. And if you look at the inlet of the pump, the level difference or the difference of elevation between this point and the level of water in the sump is what you call the static suction lift. I'm calling it H with the subscript suction. And this is the downstream tank to which water is delivered. And you may have a flow control valve or throttle valve somewhere here. Now, look at the level of water in this pump. This is a Z equal to Z2, and this was Z equal to Z1. This level is at a certain height above the inlet to the pump. So this is called the delivery head. And this total difference between Z2 and Z1 is what you call the static lift. So suction lift, delivery lift, and static lift. So the static lift is the sum of these two. So you want to raise the water from the lower tank to the higher tank, so you have to increase the potential energy. So when the pump is running, you are going to do some work and increase the head. So we can use the extended Bernoulli equation, which is a static flow energy equation in disguise, where there is no heat transfer term, but there will be a head loss term. So look at a point 1 on the surface here of this tank and a point 2 on the suction. And suppose those points are on a given streamline from this point through this pipe, suction pipe into the pump, through the and so out through the discharge pipe to this point. Okay. Then the total mechanical energy at point 2 will be the total mechanical energy at point 1 plus the energy you're adding to the pump, the head pump minus the head loss. Now, both 1 and 2 are exposed to the atmosphere, so P1 and P2, those pressure at 1 and 2 will be equal to the atmospheric pressure. So this term, first term on the left hand side and the first term on the right hand side will cancel out. And usually the surface area of the tanks will be large. So V1 and V2, the velocity of the fluid at this surface, that is the rate at which this level is going down, and the rate at which this level is going up, those can be neglected. So the kinetic energy terms can be neglected. So you just have the difference of heads here, Z2 minus Z1, which is a static lift. So H pump will be Z2 minus Z1 plus the head loss. So this is, you can say that at steady state, the head provided by the pump must be equal to the static lift plus the losses in the pipeline and the pump itself. So this right hand side I can call the head that is required to be supplied at steady state. So H required is H static plus head loss. And at steady state, the head provided by the pump must be equal to the head required by the system or the head H required, which whatever you want to call it. You can call it H system or H required. Now, what are the losses? There will be what you may call major loss in the pipeline. Now, you know from your second year course that you can write it as a non-dimensional quantity called the Darcy friction factor into L upon D into V square by 2G. So this is meters. L by D is non-dimensional. L is the length of the pipe. So in this case, if you are looking at, there will be a length of pipe in the suction side and a length of pipe on the discharge side, and the two diameters might be different. So you have to separately find H loss major on the suction side and the delivery side. Okay. So we have this factor, length of the pipe, either suction or delivery, divided by the diameter of the pipe, either suction or delivery, into the average velocity squared. The average velocity between the flow rate by pi d squared by 4. Now the flow rate on the suction pipe and discharge pipe will be the same, but this diameter d may or may not be the same, so you have to be careful. And you have this Darcy friction factor. Now you know that when the flow is turbulent, that will occur if the Reynolds number based on the pipe diameter is larger than a critical value. So for natural transition, you know the value is about 2000 or 2300, the critical Reynolds number. And Re subscript d is the Reynolds number where you're using the average velocity through the pipe and the diameter of the pipe. So F depends on Red and this epsilon by d ratio when it's turbulent, and is given by Moody's chart. So on a log-log plot, if I plot the friction factor versus Re, for Re less than the critical value, you have a straight line here on a log-log plot, which represents the friction factor for laminar flows when Red is less than the critical value. So if you solve the Navier-Stokes equations, you will find that it is 64 by Red. So log F will be log 64 minus log Red. So if you plot log F versus log Re, it will be a straight line. Conversely, if I can plot F versus Re on a log-log plot, okay, it will be a straight line. And it is turbulent, you have flows like this for different E by D ratios. So as E by D increases, the value of the friction factor increases. But what you see here is that when the Reynolds number is large and the pipe is rough, the F is roughly a constant. Okay. So for high RD flows in a rough pipe, F is almost a constant. And this constant value might be given to you in a problem. Now the minor losses due to valves and bends are some loss coefficient which will be specified into V square by 2G. So what is the total head that is required? We have the static lift, which is a constant, and if you look at the head losses, both are proportional to Q squared, because in practice the flow is highly turbulent and F, the friction factor, is a constant. So major loss is also proportional to Q squared because V is proportional to Q. So if you go back and look at this, okay, if F is a constant and V is proportional to Q, then head loss will be proportional to the flow rate. So the H that is required is of this form: H static plus A times Q squared. Now the value of the A in the coefficient representing the flow resistance, it may be changed by using a flow control valve or a throttle valve. So if you go back and look at this figure, if you close this valve partially more and more, okay, you're increasing the flow resistance, and therefore A will increase, the value of the coefficient that I'm calling A. Now if you open the valve partially, then A will decrease. So when the valve is fully open, A will have the minimum value. Now let us look at the steady operating point. Suppose I have a pump characteristic shown over here, and the head required, the system characteristic, is H static plus AQ squared. So if I say this is the origin, then this vertical intercept here is your static suction lift. Okay. So you notice one thing, that as Q increases for a given A, the head required will increase. So the more the flow rate, the more will be the head that is required. And that will have to be supplied by the pump. And the slope of this curve is always positive. The slope of the pump characteristic may either be positive or negative. So I have shown a case where it is both. And this is the intersection point. So when the pump is running at steady state, the energy balance showed you that intersection point of what you may call the system characteristic, that is the head required, and the pump characteristic. So if I change the throttle valve setting, I'll change A, then I'll get another curve, and the operating point might shift. Now this operating point may be stable or unstable to small disturbances. If the system, so suppose I increase the flow rate slightly and then decrease it back to the old value, will the system come back to the original state? Or if I reduce the flow rate slightly momentarily by opening and closing a valve and then put it back to the same flow rate, will you come back to the same point? If you do, then it's stable. Otherwise, it's unstable. So we'll show that if the curve has a peak, then it's unstable. So note first of all that the slope of the HQ curve for the external system is always positive. That I've already shown you. Whereas the slope of the HQ curve for the pump may be either positive or negative. So first we'll look at a case where the slope of the pump is positive. Now we may have a case where at the intersection point the slope of the pump characteristic is larger than the slope of the system characteristic. So let us say the pump is operating at this point, which I've called where the flow rate is Q1 OP and the head delivered by the pump is H1 OP, and the head required by the system is also H1 OP. Now suppose I open a valve momentarily and increase this Q operating, so I'm moving to the right of this point. Okay. Now what will happen? The pump head will rise. So there's an excess head now. If the pump head is more than the system head, it will tend to increase the flow rate further. So you will tend to move away from the operating point. So it is unstable. Likewise, suppose I close the valve slightly and reduce the flow rate. I move to the left of this point. Then the pump head reduces. And because the pressure increase in the pump is lower, it will tend to reduce the flow rate further. So you will not have a tendency to go back to this point. Furthermore, as you can see, this kind of a curve is intersecting at 2 points. So if you change the flow rate, you may go from one operating point to the other operating point. So what might happen is there is a possibility that the pump will oscillate between the two operating points. So you can use this term hunt or surge to describe this case. Okay. So pump surge is an oscillatory condition where the pump hunts or looks for a steady operating point. So such instability is undesirable. So we must make sure that if the pump characteristic has an unstable part, it should be outside the normal operating range of the pump. Now let us look at a case where the pump characteristic is negative. Okay. So here I have shown the intersection point as A. So let us say you are at this point. The flow rate is QA. Now suppose I increase the flow rate slightly. Then what will happen? The pump head will decrease. So if the pump head decreases, it will tend to reduce the flow rate. So you will have a tendency to move back from point A towards point B towards point A. Conversely, suppose you were operating at point A and momentarily the flow rate is reduced, so you move towards point C. Now what will happen now? The flow rate is reduced, but the pump head has increased. So when the pump head increases, it will tend to push more fluid through it. So the flow rate will tend to increase and it will move from point C back towards point A. So this is a stable operating point. Okay. So you would like the pump to operate at a operating point where the slope of the pump characteristic is negative. If the slope of the pump characteristic is positive, okay, you may have instability or some kind of oscillation. So this is what I introduced last time as surging. Today I have talked about it in more detail. Now let us go back and look at this outlet diagram, velocity triangle, and how the blade angle affects the efficiency of the pump. So I've drawn 3 diagrams here where the pumps are rotating at the same angular speed and the volume flow rate is the same. So if the volume flow rate is the same, then the radial component of velocity, which some people call the flow velocity, is the same. So I forgot to write the superscript flow here, q by 2 pi r2b2. Now the absolute velocity squared at the exit is the square of Vr plus square of Vt. So what is Vt? It will depend on the shape of the impeller blade. For the radial blade, you see that Vt2 is the same as u2, which is r omega. And if it's backward curved, then Vt2 is this much, which is less than u2. And if it's forward curved, then this is V2, and this is Vt2, which is larger than u2. Okay. So the tangential component for forward curved blades is larger than omega r2, larger than u2. And for backward curve is less, and for radial blades they're the same. And if you have a case, let us compare 3 pumps, one with a radial blade, one with a forward curved blade, and one with a backward curved blade, which is running at the same angular speed and the flow rate is the same. In that case, Vr will be the same, but Vt will be different, so the V square will be different. And V square at the outlet will affect the efficiency of the pump, because the larger the V square, the larger will be the losses in the volute or scroll casing. So which will have a larger V2? Well, as you can see, the forward curved blade will have the larger V2. The length of this arrow is the largest for the same Vr. So the vertical line here is the same, because I've shown the velocity triangles at a point where the tip of the impeller is radial. Okay. So for the same flow rate, the vertical line is the same, but the swirl velocity component is maximum for the forward curve. So you have the minimum for the backward curve. So backward curve vanes will give you least value of V2, the absolute fluid velocity. So the dissipation of energy in the volute will be less when the blades are backward curved. So the efficiency of the pump is higher. But of course the head will be less. Forward curved blades will give you the maximum head, but the efficiency will be less. The other thing to note is for forward curved blades, the slope of the HQ curve is positive, so there may be surging. Okay. If you have a backward curved blades, you have a further advantage, a more important advantage of having a negative slope of the characteristic curve. So the operation is stable. There will be no surging. So most centrifugal pumps will have backward curved blades for 2 reasons. One is the efficiency of the pump will be larger and the operation will be stable. Now let us look at the flow in the volute casing. Now once the pump has left the impeller, there is no torque on the pump, no torque on the fluid particle, except frictional torque, but we are using an inviscid model where there are no frictional effects. So in that case, the moment above the center line is 0. So if there is no moment acting on the fluid particle, its angular momentum will remain the same, invariant with time. So r times the tangential velocity or swirl velocity in the volute will be a constant. This is the prediction of inviscid flow theory. So the fluid particles will therefore follow a path along which r times v theta or vt will be constant. So this equation is similar to what we must have studied in your second year course as the irrotational line vortex, which is also called free vortex, as opposed to the force vortex where Vt is omega r. So here Vt is a constant divided by r, and you can show that that is irrotational. Now you can also see why it is called a free vortex. In the case of a force vortex, there must be an external torque which must be supplied, and some energy will be consumed in the process. Here there is no torque, so you are not providing any external energy to maintain the flow, so it is called a free vortex. Now, the one theory that we have considered is one-dimensional, so we are, in effect, although we may not state it, assuming that the number of blades is infinite and the gap between adjacent blades is infinitesimally small. So in that case, the radial velocity coming out of the impeller is independent of the angle theta, and it is simply given by Q flow by 2 pi r times B. Now, this is a kind of source flow. You must have studied inviscid flows in your second year, and you might have studied a line source, where you imagine that the fluid is coming out of the origin with constant flow rate. So in the volute casing, your VR will reduce as 1 upon R. Okay. And what will be this Q flow? Well, Q flow, you can see, is 2 pi R2B2. That is the flow rate at the exit of the impeller or the entry to the volute casing. So VR then is VR2 times B2R2 by VR. So it is inversely proportional to R. So the flow in the volute resembles a flow that you might obtain by superposing a line source and a line vortex, irrotational line vortex. And if you look at the stream lines and the path lines, you will see that it will be a kind of spiral path, which is a logarithmic spiral. That is not difficult to show. So the pattern of spiral streamlines should be matched by the shape of the volute, so that the flow conforms to this kind of a flow. So that is why the shape of the pump casing is in the form of a volute, which is a logarithmic spiral. So this is your inviscid flow design. Now it is almost 12 now. Are there any queries? Now there was a request to extend the deadline for the assignment. I have not yet done it because I was busy and I need to figure out how to do it. I'm not that familiar with Moodle. So do you really want more time? I can extend it. There's no problem. So I'm stopping the recording.